Oh, that was nasty. I hate to see.
So, I have a confession to make. Do you guys like Taco Bell? I mean, tacos there are I don't know, they're like approximations of.
Have you tried the taco burrito?
Is it good?
I've seen ads for it. I don't know.
No. I don't know that I've been to Taco Bell in the last decade of my life. But yeah, I do have a confession to make. Okay, so this is our last unit, and I mean, I know you. So I mean, I say this like through tears, but I just have to admit that they're not. I may have doctored the photos a little bit. I hate to burst that innocent bubble of yours, but I just was telling you that because like I haven't been to Taco Bell and I don't know how to lie about it. You know, like I just haven't been there, and this image is as fake as the tacos are. So I just had to share.
Well, now I'm going to have to buy the Taco Bell.
Now don't tell anybody that the images are fake, because I mean, what we have here are like very believing people, and you guys. Anyway, I just feel like we may need to have like exercises where we rebuild trust between you and me. And
trust fall, Mr. Chase.
Trust fall. But we are gonna start at least wading into sequences and series a little bit today. You have your blue sheet in front of you that gives at least as usual the tentative schedule. We'll see how that plays out.
Don't feel bad.
I think we did obey the schedule at least once or twice this year. Yeah.
Don't feel bad, Mr. Chase. I can always go climb a Taco Bell sign and write out here and
Yeah, you could actually. One of these days, I am actually going to have to go do that. Have like the manager. Hey, can I get the thing and the letters? Okay, I'll be right back in 20 minutes. And then what? Then you'll be like, wait, he really did do it. Okay, good. So let's say something about sequences, and then in the coming days about series as well, and we'll understand maybe what the difference is between those words. That'll be wonderful. So informally, I have this kind of defined informally first, and then more formally as the second sentence here. So informally, I think we all understand a sequence to be like an ordered progression of numbers of some kind. But more formally, or rather, in terms of things you've thought about before, a sequence is just a function, that's all. It's just a function. We've dealt with functions lots and lots already, and this is just another function. The only thing special about it is it takes as its domain the set of all integers, or possibly some subset of that. Maybe just the natural numbers, the whole numbers. But the point is, like, for sequences, I think we all have, even before I tell you, we have the sense that like we can talk about the 5th term of the sequence or the 6th term, but we can't talk about like the 5.3rd term or something, right? That doesn't make sense to us. So that's why that's the only conceptual restriction, and we're placing it on ourselves.
I was just going to say, like, what if there was a sequence that isn't a function, but then would that not be a sequence because it's not working?
I'm not sure what you mean.
Like, if you have a set of numbers that, like, you said a sequence is a function, but if you have a set of numbers that what's
ordered is important. We need to be able to pair them with the integers, right? Yeah, it's important that we ask, like, not that you just be like 17 is in there somewhere, but that you be able to say like 17 is the whatever, the 5th number in the sequence. So the ordered is actually not just kind of a cosmetic word in that sentence. It is. Those are two definitions that are equal. Just the second one is slightly more formal. You have a couple different ways to write them there. So you can notice too, this is not an accident, that this one is a finite sequence, and this one here, for example, with the triple dots at the end, just continues on forever. It's an infinite sequence. You can see the different notations we might use. Here's like kind of your typical set builder notation used to define this nice sequence. Sometimes the explicit rule is like sitting there ready for the taking. Sometimes it's not as obvious, but you could derive it quickly if you needed it. Anyway, so I think these are all notations perhaps that you're already familiar with, I'm not sure. Am I right that you had some prior experience with sequences? Perhaps in algebra 1 maybe. I don't know if in algebra 2 very much, but perhaps, yeah, I assume you've seen at least a large part of what we're going to look at today, but we'll see. Yeah. Okay. Was that too fast? There's nothing special about these particular examples, by the way. defining a sequence can be done in two ways, and already you've kind of seen some of that here on the previous page. One way would be to do it like we've always done with functions, and that's to give an explicit rule. I think you've heard these terms before. This is easy then to generate the 5,000th term, if you like, right? The 5,000th term is just 5,000 squared plus 2, right? Easy, easy. Whereas the second way of defining it would be recursively, and an example would be something like this, where we need both elements of this rule. And again, I think you've heard the word recursive in your prior math classes, but let's just let's remind ourselves what we mean by that. We mean that the rule defines a given term in terms of previous term, one term, or maybe multiple previous terms. And already, I think if you've had any experience with these two kinds of rules, you already know the explicit formula to be more desirable and more powerful if it can be made available. However, there are lots of very, very useful and important recursive relationships that naturally arise throughout the universe that can't really be nicely given as explicit rules. A very famous example of that would be something like the Mandelbrot set, which is a very, very complex fractal that, but it's generated by a very, very simple rule, very similar to this, except with a squared, with complex numbers on the complex plane. So, I mean, you could, if you have even, a day's worth of experience with your favorite programming language, you could probably code up the Mandelbrot set in like 3 lines of code. And it has like just infinite, beautiful complexity. Like you can zoom into this place and find places inside of it that are just like complete like foreign land. It's amazing. You know what I'm talking about, the Mandelbrot set? Seen the Mandelbrot? You don't know what? No, I've got, all right. Well, yeah, time for me to pull up. I just assumed everyone has seen the Mandelbrot set before. I'll show you. You've never seen?
No.
No, but I want to.
No, all right. We'll show it to you in a minute. It arises from a very, very simple recursive rule, like many other things in nature too. In fact, people who do computer graphics often use recursion to generate pictures of clouds and ferns and whatever, water, motion, and all sorts of things, but they can't be described explicitly necessarily. It's a very, very complex, in fact, this kind of relationship even gives rise to something you've probably heard of called chaos, like all different kind of chaotic behavior happens using recursive rules, but they can't be necessarily given as explicit rules. This, though, however, is a very, very simple rule, isn't it? So I think you can understand how that one's done. And you understand, too, why it's necessary to give not just the recursive rule, but also with it the initial condition. Otherwise, you don't have a rule that can generate a sequence. You need both. Ian, yeah?
Perhaps people may have heard more of the Fibonacci sequence, probably not as many.
Yeah, I mean, the Fibonacci sequence is defined in terms of two previous terms. I think everyone's probably heard of the Fibonacci sequence, right?
One,
and it's not there. It's actually not impossible to come up with an explicit rule for the Fibonacci sequence, though I'm sure you've probably never tried. But it is possible, and you should challenge yourself to do it. I don't know. That's a very challenging problem. Come up with an explicit rule for the Fibonacci sequence. Yeah. Well, except it's already been done. You can look it up too. What's an arithmetic sequence? Let's review time. Yeah, you add something each time. We call that thing you add each time the common difference. We'll call it D. And of course, the common difference could be a negative number too. So like this sequence could be going downhill, I guess. Yeah. So the recursive rule is quite simple. I think we don't need to necessarily even say it. It's this, right? It's each term is equal to the previous term plus the common difference. Where again, as always, we have to define what A1 is also, of course, right? The explicit rule, let's work through quickly with the example that we had on the board up a second ago. What was it? A1 was 3? I think A1 was 3. And AN was AN minus 1 plus 5. So what does that look like? 3, 8, 13, 18, etc. Now I want you to really think hard as we come up with this explicit rule. how would you generate like the 20th term of this sequence here? To generate, let's stop and think hard about, we'll do the 20th down here. How would you generate the second term? What would you have to do to 3? You have to add 5 twice, right? So to get the 20th term, what do you need to do? You need to start with 3 and add how many 5s? Yeah, we have to be careful. Stop and think before you answer. How many 5s do we have to add? Is it only 19? I mean, if we're considering this the first and the second and the third term, the fourth, etc., then I think you're right. To get the second term, we only had to add 1 5. To get the fourth term, we only had to add 3 5s, right? So, in general, what's the rule then for an arithmetic sequence? The explicit rule. I'll do the first part for you. It's A1 plus, all right, you do the rest. D times n minus 1. And I hope you see where you came from on that, right? Like, so if this is not the kind of thing we need to memorize. I mean, I hope that you'll use it enough that it'll be on the tip of your tongue. But if there ever were a moment of like of failing in your life, you just look back to this kind of thought and just think through it again. Of course, that makes sense. We're just adding a bunch of copies of D to the first term. That's all. Okay, well, let's try this with an example. With a couple, 2 arithmetic sequences. And I'll call a couple people up to answer these questions in a minute. Okay. Do them all. And you'll be ready. Your name might be among them. You can't do it. I can't tell you. Think about all the stress that produces in your life. Could be anything. Which one should I make you do? That's my goal. Produce lots of stress and stuff. get done with these? I mean, you can get the explicit rule first, but when you're ready, you can do the. That second one, arithmetic, for real? Why is that so? Isn't it a key problem? You're gonna get it. What's log 6 minus log 2? Amber, would you do 2A? You like that one?
I don't know. No, I don't.
I'm giving you a tricky one there. So before Camber writes the answer to number 2A, I don't want to like destroy this for anyone. Does anyone want another minute here? I mean, to think about it. I mean, this is kind of really just cool problem, right? Explain yourself to Camber while you're there.
So if you were to add, say, log 3 to log 2, when you put them together, you multiply the 3 by the 2, and you get log 6. And then if you add log 3 to log 6, when you put them together into one thing, you multiply 3 and 6. It's just properties of logs.
So it's just properties of logs. Don't trivialize it, though. So there's some people who might forget those properties. So I just throw that out there. You know? All right, well, let's finish it off. Let's get Eric for B and Zoe and Claire. Then when you're ready. Eric, Zoe, Claire. When you're ready. Yes. Those properties. I do have candy, but I really love the luxury. I give them the charger. I don't have to think about anyone else. This one?
Yes. I have no idea.
Okay, let's hear from. This is interesting here. Yeah, so this does turn out to be arithmetic, I guess. And I like how I want to make a few comments about the things I see here. I like both on these two here that we have A1 listed. This is A10. Did you guys? I guess I should ask that first. Does everyone agree that this is A10 over here as well, and that this is D here and this is D here? Okay, and these rules are the same as the ones you got? Okay, review, part 2. What's a geometric sequence? Can someone bring back to mind what we mean by a geometric sequence? Yeah, I think this should ring a bell, but yeah, we'll call it a common ratio this time. Just like last time we called it a common difference because, well, I guess the point is we should be able to tell when we have an arithmetic sequence in the wild, because if you see the sequence and take between each term the difference, one term minus the previous one, you should always get the same common difference. Likewise, with the geometric sequence, you'll know what you're dealing with is geometric if you take one term and divide it by the previous, and you always get the same number. Now, just like D can be either positive or negative, to make it go uphill or downhill. You said a second ago that a geometric sequence is one that either multiplies or divides by a common number. I only said multiply here because obviously if you wanted to like divide by 2, then you just need to make r be 1/2. Right? So the recursive definition, I think, is fairly clear again here. It's just you're multiplying each term by the previous term. Excuse me, you're multiplying r by each previous term to get the next term. The explicit rule, let's have the same conversation again. Let's pretend this time we have the sequence 3, 15, 75, 375. I don't know, right? So what's the rule here? And again, I guess my question is, how do we generate the 20th term of that sequence? It looks like, again, how would you, let's ask the question, how do you generate the third term? What do you do? You multiply 3 by some stuff. What do you need to multiply 3 by? Yeah, 5, twice, right? Like 2 copies of 5. So how many times do we need to multiply 3 by 5 to get the 20th term? What'd you say? Yeah, 19 again. I feel like we've had this conversation, right? So how is an efficient way to write that here? Repeated, just like last time we had repeated addition, we said, let's do that quickly by doing multiplication. Just the same story here. Instead of repeated addition becoming multiplication, we have repeated multiplication becoming like exponentiation. So what's the general rule? Can you say it before I put it up here? What's it going to be? AN equals A1 times... Great. You're phone me. I'm hoping. I hope. Good. So, good. Again, if you're stuck in a dark hour of your life and you don't remember this formula because you're like, I didn't memorize or I forgot it or I can't remember if it's an n or n minus 1, just think read first. And then think clearly about the situation. Like how does this come out again? How did this work? And do whatever makes sense and seems to be working for the situation, right? Does it generate, if you produced a rule that operates faithfully, then you've done it, right? Well, unsurprisingly, let's do the same practice task here. And if you didn't get to come up last time, well, maybe this will be your lucky day. Yeah, come up whenever you're ready. Finding out. Matthew 2. All right, are these answers as they come up ones that you agree with? On number 1, they're all up there now. I don't know, ask someone here. Franklin's not so sure about himself. Can you just give him some love?
I'm doing
C, I think, yeah, okay. Who did I call for A? Cheyenne? You got it. You got me. Okay. All right, well, I gotta pull up. Can someone Google the Mandelbrot set? You don't know how to spell it, though. Oh, I got you. Mandelbrot.
Play it on the computer. Alright, time out.
Images. Is it okay?
No, I can't see the board.
Yeah, so these are pictures of the Mandelbrot set. This is the typical zoomed out. This is the origin on the complex plane right here. And these are different regions. They're crazy places inside the middle. And then when you zoom in on the boundaries, this is the kind of shape you get. When you zoom in really close along the boundaries. Crazy stuff. Isn't that insane? I just Googled Mandelbrot. And if you zoom in different parts of it, you get completely crazy behavior. Did anyone else Google the Mandelbrot set? Google image that thing, man.
Oh, I know what that is.
Have you seen this? It has all the same complexity to the borders.
Yeah. Oh no, I did that one. It's usually like, I have to do that.
Yeah, and as you zoom into the borders, the boundaries, you get all sorts of like crazy.
He's not there anymore. He went like 10 years ago.
It's called the Mandelbrot set. It's a fractal. It's the complex plane, and then you have, well, but it applies a very, very simple recursive rule. It's just like, take a number, the complex number, square it, and add a number. And then take that output, do it again. Square it, and add a number. And if that converges on a point, then it's in the Mandelbrot set. If it escapes, it's not. If that like diverges really quickly off to infinity, then it's not in the Mandelbrot set. All right, let's wait, hold up. Were there any thoughts about that here? Let me say one thing here too briefly. This is cool to me. One other, just you don't have to do this, but just for fun, this is certainly one way to rewrite this if you wanted. Just like I said, just for fun. Do you agree that this is this? Okay. So we could write this as -2 to the n minus 2. Wouldn't that be a tidy rule for this? That'd be cool. Are you not impressed? Okay, sorry. I thought that was worth saying. Okay. The other thing I thought would be interesting to harken back to is, do you remember this problem a second ago? Log, yeah, you do. Log 3. Log 6, log 18 is log 2, etc. Log 54, right? Remember that problem? The explicit rule you found was log 2 plus n minus 1 times log 3, yeah? What did this feel like when you were doing this, even before we talked about this stuff? Yeah, didn't it feel like a geometric sequence? Do you remember your log properties? Yeah? What's the rule, what's the explicit, now that we've talked about geometric sequences, what's the rule for this sequence here, 2, 6, 18, 54? Isn't it 2 times 3 to the n minus 1? Which is equivalent to this, I mean, with the log of that thing. So the log of a geometric sequence gives an arithmetic sequence. I think that's an interesting thing to notice. And now's a good time, I think, to also stop and say this. What are we really talking about when we're talking about an arithmetic sequence? What kind of function? Yeah, and what kind of function are we really speaking about when we're speaking about a geometric function? A geometric sequence. Yeah, an exponential function. So maybe this is then not a surprise, but when you take the log of an exponential, you get a linear. In fact, you might have to do that on like the test tomorrow, right? Taking the log of, does that sound familiar? Taking the log of an exponential function to get something linear. I just like to make those connections. I'm done now. Okay. You don't? Is that what you said? Okay. All right. I digress. All right. There are some problems that you'll encounter in tonight's practice that will be, that will not always give you, like in the last couple problems, the first term and the common ratio, the first term and the common difference, right off the bat. Sometimes we'll give you the first term and the seventh term. You'll have to figure it out. Sometimes we'll give you the common ratio and we'll give you the fourth term. And you can come up with a rule. Or worst case scenario, this, where I give you neither the first term or the common difference and common ratio. So there are lots of things to do in this problem. Let's do them all. So let's first suppose the sequence we're talking about is arithmetic, with A2, 3, and A5 being 24. So give it a second of thought, and then we'll see if we can come up with like a systematic way to come at this kind of a problem. You might just be able to kind of noodle your way into it. You know, it's just kind of like, I don't know, just make a guess. Yeah, you kind of can maybe make some guesses and be like, well, I think this is. So use both intuition, but then also see if you can come up with a systematic way to do it too. Maybe you can make some educated guesses, and then maybe you can also come up with like a algebraic method. Already some people are having some thoughts. What's your line of attack with people who are working on A here? This is arithmetic. Have you figured out what the common difference is yet?
Negative 4 plus 7 is the answer.
I want methods though, not answers here.
Ran my head into the wall until it worked.
Oh, that's one method that may or may not produce results for all of you. Does anyone have a thought that can help us like crack this a little bit? Yeah.
Well, for the, at least the arithmetic one, or for both, you know that you're gonna have two more terms in between. So you're gonna have 3 segments in between 3 and 24 to get your 2 terms. So for instance, for arithmetic, you divide the difference between the 2 terms of that by 3.
Yeah, yeah. You see, like you have to have a span of 21 to cover in like 3 hops is kind of the intuitive thing Amber's saying. So already maybe you have a way in. Let me provide this symbol-heavy description that meets your same criteria. But I think that you'll see it's exactly what you just said though. 24 is what happens. I don't know what. Let's say let's pretend for the time being that I don't know what A1 and B are. Okay. But 24 I do know is what happens when I do A1 plus 4 copies of D. Do you agree? It's like the definition of the 5th term is the first term plus 4 copies of the common difference. Similarly, 3 is what I get when I take A1 and add 1 copy of the common difference to it, right? Well, now what do we have before us? A very simple system of equations. And notice the way I'm about to solve it exactly mirrors what Camber just said. Isn't the distance between these 21? And isn't the number of terms that we need to kind of hop through is 3. So I hope you see how the formalization here connects with the intuition that tells you that this should be 7. I hope you see the connection there. Once you have that, then the game is up, right? What's A1 then? What's A1? Good. So then I think we've had plenty of practice doing this. I'll write the explicit rule. It's an equals -4 plus 7n minus 1. The recursive rule is a1 equals -4 and an is equal to 7an minus 1. Good. Now, what about geometric? Can we use a similar strategy down here? What distance do we have to cover here? The answer is this time not 21, but what? We're not measuring in like additive distances. We're measuring like multiplicative distance now, right? So we need to cover like a multiplicative distance of like 8, right? So maybe we can kind of reason to that too. A1 r to the 4, A1 r to the first. This time subtraction's not maybe going to help. What are we going to do? Yeah, and that's kind of what you just did a second ago. We realize we have a distance of like 8 multiplicatively to cover, and we have 3 jumps to make, so r must be all right. What's A1? 3 halves. Write the explicit and the recursive rules. I won't do it because you're losing interest. Okay. There's one other thing I would have liked to have said to you, but I think it seems like you're done, so we'll just call it good. Homework, I was going to mention something about the limit of a sequence, but I think you'll be all right. Yeah.
But it's going to be once around the 37.
But you'll be all right. It's just like taking the limit of a function. Do your best, Annabelle. All right. Homework 1 will be discussed on Wednesday, so feel free to procrastinate until tomorrow night if you like. Unless you know you're really dying to get it done. Fine. Friday? Yeah, we have a quiz on this Friday. All right, I love you all. Bye. See you tomorrow for a test.
I got to stop. Well, Dusty, what did you want to test, Mr. Chase? Yeah, I missed
Maybe I should use boundaries, but I mean, it doesn't really matter too much.
Right, but I was prepared to risk it.
Yeah, you don't have to label. Yeah, I don't think we label it. Yeah, just make it as accurate as you can. You know, technically it's the boundary. Okay.
Do you mind if I have something to do right now, but...
Or you do, what, oh, do you have something to make up?
No, like, I just have, like, another thing, like, for,
I know, but you need to make something up for your
no,
question.
yeah, if I had, like, questions on the test quiz, I come in.
Yeah. When are you coming by?
I think I should get done around, like, 3:15.
Okay, I should still be there. Yeah.
Okay, great.
Cool. See you in a little bit.
Yeah.